So this is AP Calc section 6.1. It's on antiderivatives and slope fields. So first we'll start with the indefinite integral, which is written like so here. The indefinite integral has no limits, so this is just blank. And the solution would be the antiderivative, big F, plus c. So when you don't have limits on your integral, you have to add c. And the reason you have to do that is because all the antiderivatives differ by a constant. Because, and we may have already talked about this, but like if you have, say, there's your function. So yeah, your antiderivative is your function. If you were to shift it by c, so this plus c is a vertical shift, both of those, these are the antiderivatives, big F. This is big F with a different c than that one. Both of these would have the same derivative because they have the same shape. So that's why we have to add the c when we take an indefinite integral. Actually, I was going to go back because I'm just kind of looking at my notes right here. So this whole thing is the indefinite integral. This is the antiderivative. And then this, of course, is the constant. And then this whole thing is the indefinite integral, all of the possible translations of it. So, if you have something like this, all you have to do is find the antiderivative, so that's 3x to the 4th over 4, and then since it's an indefinite integral, you just add c. And then here are some rules, some the integral rules or antiderivatives. And the first one we already know because we've been using it. And this next one we've talked about, it came up in the homework some time ago. But can you think of a function whose derivative is 1 over x? And that function would be natural log. But you have to add c, of course. And it's make sure you do the natural log of the absolute value of x, because if you recall a logarithm, or natural log in this case, its domain is only from x greater than 0. So you cannot take the natural log of a negative. So that's why you need to put the absolute value of x there. And then this one, if you try to do it by hand, so I'm just going to do, we'll do e to the kx dx. So think of a function whose derivative is e to the kx, and that's itself e to the kx plus c. But if you try to differentiate that to check it, if you differentiate that, that's e to the u, so that's e to the kx, but you have to use the chain rule times k, plus, and then the derivative of c is just 0, so that's gone. So, but this doesn't match the original integrand, so we have to adjust it. We don't want that k in front, so we adjust it by dividing by k, and then it will match. So you have to, when you do e to the kx, you have to divide it by k. And you can see there's the rule. And then think of a function whose derivative is sine, and that's cosine, but with a negative. And you also are going to have to divide by k because of the chain rule there. So it's negative cosine of kx over k plus c. And we will need to memorize all these. Fortunately, these aren't too bad because they're just the inverses of the kind of the opposite of the ones. Opposite's not the right word, but hopefully you know what I'm trying to get at. And then the integral of cosine of kx, think of a function whose derivative is cosine, and that's going to be sine. And again, we have to divide by that k. Whoops. Okay, what function has a derivative that's secant squared? And that's going to be tan. Notice on these last 4, they don't have the kx's in there, so you don't have to worry about those. A function whose derivative is cosecant squared, that's going to be negative cotan. of x plus c. And then the derivative whose function, or a function whose derivative is secant x tan x, that's going to be secant x plus c. And then the last one's going to be negative cosecant. So we will have to memorize all of these. And here are just a couple where you can practice them. So the function whose derivative is cosine is sine of x over 2. And then we have to divide by k. The k is 1/2. So since I'm dividing by 1/2, that's the same as multiplying by the reciprocal 2. And make sure you add c. And you can check it by differentiating. So let's go ahead and check it in a different color. So I'll bring the 2 along. The derivative of sine is cosine. And then times, use the chain rule, the derivative of x over 2 is 1/2. And the derivative of c is 0. And then these 2's would cancel, and you would get cosine of x over 2, which matches the original. So that's how you can check these, especially if you're not sure. Okay, this one's just a polynomial, so that's pretty straightforward. So I'm going to go back to blue. So this is going to be x to the 5th over 5 minus 3x squared over 2 plus 7x plus c. Alrighty, this one is a little interesting. It says evaluate using a calculator, and it doesn't give us any limits. So it's like, okay, what are we supposed to do here? Well, let's think back for a sec. Well, at the very beginning, the very first slide we had, we saw that the integral of a function is its antiderivative plus c. And we also, if you look way back at the Fundamental Theorem of Calc, Part 1, and by the way, I do believe some books might call the Part 1 the Part 2, so just know, anyway, our book says big F of x is the integral from a to x of f of t dt. So that's if you look way back. Sorry, I'm going to sneeze. So what that means is we can put together these two formulas into one and say that the integral of f of x dx is the integral from a to x of f of t dt plus c. So now let's talk about our function. So, well, it's just going to be the integral. Now a, since we're going to put this in our calculator, we could choose any a we want. We do need to make up a number though. So I'm just going to use 0 because it's easy. And then x. And then f of t dt would be t sine of t dt. Okay, now to put that in the calculator. It's going to have to, oh boy, how am I going to move that? It's underneath that. Okay, I can move that thing. Alrighty. On y equals. So in y, oh, by the way, we're going to graph this in y equals because we're going from 0 to x here. We're not going to get one specific value. So if we were doing a definite integral, we would have actual numbers for both of these, and we would get one number, one value as our integral. But because it's indefinite, we are going to have a curve. Because remember earlier I was showing you that the indefinite integrals are a family of functions, a family of curves that differ by a constant. So when we do it this way, we're going to get a curve. So I'm just going to go ahead and input this part right here in my calculator, Math 9. Of course, on the 84, it's going to look a little different. On the 83, we put in x, sine of x, comma, 0, comma, x. And I'm gonna try, I think a trig window since it's sine. I'm gonna do zoom 7. Oh, cool. I have a fast calculator. Your calculator might be a little slower. Definitely pause this and try it on your own. Make sure that you can get your calculator to do this. Now, what happens if you use a different a value? What do you think is going to happen? Guess and see if you can guess what's going to happen. So what I'm going to do is I'm going to go back to y. I'm going to go down to y2. I'm going to put it in again. Math 9 x sine of x comma x comma, and I'm going to use a different a value. How about 2 comma x? And let's see how that compares. Oh boy, it looks like it's going to be a vertical shift. Cool. So these different numbers here for a affect the c value, don't they? In other words, you're still getting all of these. This is all the antiderivative. They're all going to have the same shape. They're just going to be shifted vertically. Okay. So a different a value will produce a different vertical shift. I'll just say a vertical shift. Great. So, got that one taken care of. Now the slope field, we're going to do a lot of this in class because we have a computer or calculator program, and my Promethean calculator doesn't have the program. So we will do a lot of this in class, but I just want to kind of go over it right now so you have an idea. So a slope field for a differential equation, and the differential equation is a derivative, so dy dx is obviously a derivative, is a plot of short segments with slopes for a lattice of points in the plane. And that probably doesn't make a lot of sense, but so we'll do an example. Actually, I was going to do the example in class. Sorry. An equation containing a derivative is a differential equation, so that's good to know. And with these slope fields, so the slope fields describe the derivative. The solution curves, which are the function y, so the solution curves are the y, those are actually hiding in the slope fields. And if you get good at it, you can tell, you can get a feel for what they are. So this we're going to do in class. We're going to make a slope field. So just so you know, if you can't be in class, I'll just do a couple of examples so you can see how you're going to do this. Let's say I randomly choose the point 2, 1. So that means x is 2 and y is 1. So if I plug in 2 for x and 1 for y, I'm going to get dy dx equals -2 over 1. So that means for this point right here, the derivative or the slope is -2. So what I'm going to do, -2 is a fairly, somewhat steep. Let's say that has about, well, it's a little, anyway, roughly, let's just pretend that's a slope of -2. It's actually a little steeper than, or I'll fix it. It's actually a little steeper than too steep there. Down 1, you just kind of roughly draw them. That's about a slope of -2. And let's say I choose the point, I don't know, how about -3, -2, this point right here. So I'll put that in there. That's going to be -3 over -2. So that's going to still be -1.5. So that's not as steep as that one. It's still negative, like that. And then what you have to do if you're doing these by hand is you have to find the slopes for every single point. And that, you can imagine, takes a lot of time. That's why we have a computer program, or a calculator program, to do it for us. Okay, so this we're going to do in class, because I cannot demonstrate it on the board with my calculator. This is what a slope field looks like, and we'll do this in class as well. So I'm just going to wait on that one. can see it's like really interesting down in here, isn't it? All right. Now, solving initial value problems. So this is a different, yeah, you know, I kind of like to do this in class because once we solve them, then we can check them using the slope fields. But what I'm going to do, I'm going to go ahead and go through these notes for if you cannot be in class. So that's, if you're going to be in class, you can stop the tape or the video right now, and we can just do the rest of this in class. So we solve differential equations by finding all functions f that satisfy it. And then, so that's going to be in general. This will be like a general solution. And then if we have an initial condition, that's like a specific initial condition, then we can find a particular solution. So that's just like one curve. This one would, the general solution would include all of the antiderivatives. And this would just be a specific antiderivative. So here's an example. So here's our differential equation. It's a derivative. And we have, this is our initial condition right here. And so what we're going to do is we're going to start by finding the general solution. And since we have a derivative, we undo a derivative by taking the integral. So we're going to have the integral of 1 over x dx. And notice we don't have any limits. So the antiderivative of that is natural log of x, and then plus c. So this is our general solution. It includes all the possible solutions. And by the way, that's going to equal y or f of x. I'll just put y here because that's what we use. Now, to get the initial, now we have the initial condition. So this is the x and this is the y. We're going to plug in e to the third for x. The plus c comes down, and the y is 0. And e to the third is positive, so I can discard the absolute value bars. I can use my log property and take my 3 out front. Whoops. And then subtract c. Whoops, that was funny. I don't know how I did that. Oh, well, by the way, natural log e is just 1. So 3 natural log e is just 3. I guess I wasn't thinking very well, was I? And then subtract 3. So c is negative 3. Then you go back and put that in up here, and you get your particular solution. It's going to be y equals natural log of x plus, well, minus 3. So you're coming back up here to your general solution, and you're plugging in your constant. And that is how you solve an initial value problem. Or solving a differential equation, actually. And then in class, I want to show how you can check this on with your slope fields. Because you'd use this equation to get a slope field, and then in your slope field, you would see this curve come out of that slope field. Okay, I'm going to do another one of those examples in class as well. So right now we'll just skip to this one. So now we have a second derivative, and we're going to go take it a couple steps because we have 2 initial conditions. So we'll just start, and we're going to integrate both sides here. And that's the integral of the second derivative is going to be dy dx. So that'll equal the integral of the second derivative. Please label your work so I know what you're doing. So that's going to be 2x minus, that's going to be x squared over 2. So negative 3x squared plus c. Then we have to use this initial condition here because we have the first derivative is 4. So 4 will go in for dy dx. This is our x. This is our y prime. So 0 is going to go in here and here. So that's just going to be a big fat 0. So we're just going to have a c there. So our c is 4. I'm going to come back and put that back in here. And that's the derivative, dy dx, the first derivative. Now we can repeat the process to get the original function y. So I'm going to take the integral of the first derivative in order to get y. That'll be y. So that's going to be x squared minus x cubed plus 4x plus c again. You have to put the plus c on. And now we're going to use this initial condition. Here's our x, here's our y. So y is 1. All these x's are going to be 0. So again, in this case, c will be over here by itself. Make sure you check to make sure this does go out to 0. It won't always necessarily end up being 0 there. So c is 1. Come back to here and put in the 1. So we started with the second derivative, worked back one step to get the first derivative, worked backwards another step to get the y. And then we have just one more example. So this is some physics. A projectile is fired straight up on Earth from a platform 3 meters above the ground with an initial velocity of 160 meters per second. Find formulas for the velocity as a function of time and the height above ground as a function of time. So we want to find a velocity function and a s of t function. I'm going to label our information. It's starting from 3 meters above ground. That's the initial position, s of 0. We also have an initial velocity, so v of 0 is 160 meters per second. So those are some initial conditions. And it's asking us to find v of t and the height above ground, that's s of t. Okay, so how are we going to start this? Well, they didn't give us some very important information, but they assume that we know about it since we live on Earth, and we know the acceleration due to gravity. So the acceleration, we'll do this in terms of t. A of t, because we're on Earth, and it is, we're doing metric, so it's going to be the acceleration due to gravity is negative 9.8 meters per second squared. So they're assuming that we know that. Now we can integrate that to get the velocity. So if you, here, let's just review this. If you have s of t, if you differentiate, you get v of t. If you differentiate that, you get a of t. So if you go backwards, if you have a of t, the acceleration, and you integrate, you'll get velocity. And if you have velocity and integrate that, you'll get position. So let's, sorry, I've got like clogged up here. Integrate a of t, that's going to give us velocity. So v of t equals the integral of negative 9.8 d of t. Okay, that's going to be negative 9.8 t plus c. That equals v. And then before we go ahead and integrate that again to get s, we need to find c, and we're going to use our initial condition for v to do that. So when t is 0, v is 160. So you can plug in 160 for v, and you can plug in 0 for t. And c actually just equals 160. That's going to happen anytime you're dealing with polynomials. But don't assume that c is always equal to this initial value, because if it's a exponential or a trig function, it's probably not going to just be that straightforward. So do be careful. So now I'm going to go back and plug in my 160 for c. Great, now I have v. So now I can integrate that to get s. So the integral of negative 9.8t plus 160 dt, I'm running out of space, so I'll try to write smaller. So that's going to be negative 9.8 t squared over 2, which puts it at negative 4.9 t squared, plus 160 t plus c. And s sub 0 is 3. If you plug in 0 for your t's, you'll see that c will equal 3. So I'm just going to take a shortcut since I'm running low on space here. That means I can plug 3 back in for c and get my position function. I remember doing this in college with our professor, working through this problem in college calculus. So you might see this again in your college careers. And we have found the formulas, so we have accomplished the task set before us. Let's see what's on the last slide. Oh, hey, we have a joke. An insane mathematician gets on a bus and starts threatening everybody. I'll integrate you, I'll differentiate you. Everybody gets scared and runs away. Only one lady stays. The guy comes up to her and says, "Aren't you scared? I'll integrate you, I'll differentiate you." The lady calmly answers, "No, I'm not scared, I'm e to the x." Haha. Good one. Love it. Great. So we're done.